Hello, grade 12. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Abutiwa Sos Ugobelawe Met. And without any further ado, let's look at these questions that we have here. Okay, so we have the National Senior Certificate, grade 12, September 2024. Physical Scientist paper 2, your chemistry paper, obviously. This was written last year around this time, and we're just going to be using it to practice for our chemistry paper, which is coming on Monday. So I hope you stay in tune all the way till the end, and then you get to practice all these questions with me. So what I want you to do, obviously, is to be active. Be proactive, practice these questions along with me, and then, let's just get to it. Okay, so we have the first question, which is your multiple choice questions. So once again, I'll be just going through the question paper in a chronological order, but then you always know what I advise for you to just start your question paper anywhere where you understand, right? So preferably having to answer your multiple choice questions as the last question when you are left with about 20 to 15 minutes until your time has elapsed. But then, okay, that is just advice. So question 1 says multiple choice question. 1.1 says which one of the following homologous series contains a hydroxyl group that is bonded to a saturated carbon atom that contains what? A hydroxyl group, right? Now we know hydroxyl group is for alcohols, so that means we'll go with option what? C. Right, then they say consider the compound shown below. And then the correct IUPAC name for the above compound is what? So before we can look at the options, let's just try to come up with the IUPAC name, right? So obviously we know that we have to start numbering from the side that is closest to the functional group. So our functional group is the double bond oxygen here. So we can say this is carbon 1, 2, 3, and then 4, 5. So all of this forms the longest chain, right? And then as we can see on our carbon number 2, we have our methyl branch there. So this is, since our double bond oxygen is on the first carbon, we know that this has to be what? An aldehyde, because it has the formal group, right? And then on the second carbon, that's the methyl. So let's check. We can see which one here. So we have two of them which are representing the aldehyde group, C and D. But then according to this, we keep considering that we have to start numbering from this carbon atom here. It means the correct answer once again would have to be C. So the methyl branch is in carbon number 2, right? Not in carbon number 4. So you don't start counting from this side, right? So the mistake here would be to start counting from 1, 2, 3, 4. That will make it 4 methyl, but that is incorrect because remember, we always number from the side that is closest to the functional group. And our functional group in this case is this, the formal group, right? So note that. Okay, so we then have the reaction here. It says, consider the reaction. The name of the reaction is called what? Is it hydration, halogenation, hydrogenation, or hydrolysis? So it's not hydration because we are not reacting with hydrogens, but then definitely halogenation because we are reacting this organic compound here with 2 atoms of the halogens, right? So that's definitely halogen will go with B. So even if we don't really go through the other options. So, okay, we have C, C, B, and then I believe at this point we have bagged ourselves 6 marks. And then let's continue now. 1.4 now says, consider the vapor pressure against temperature curves for 3 chain isomers under standard atmospheric pressure. And then consider the statements meant to say regarding the curves for the 3 chain isomers. Then here we are given this statements. Compound A has the shortest chain length. The boiling point of compound B is T2, okay, and then compound C is at a gaseous phase at T2, okay, And then which one of the above statements are true? Which ones are true? Then compound C is at a gaseous phase at T2. At this point, nah. Nope. It has to be at a gaseous state after it has reached a vapor pressure of 101.3 kilopascals. So they just rounded off to 101, but then it has to be a gas just right after this moment here. So this is number 3 is false. And then compound A has the shortest chain length, considering that it has a higher vapor pressure, because as we can see here, at a very low temperature already it has reached its vapor pressure. So this would be true. Okay. So with a shorter chain length, that means weaker intermolecular forces and therefore what you call a higher vapor pressure. Then the boiling point of compound B is at T2. So at that point, that's where we have the boiling point. So this is also true, right? So we are looking for an option that is number 1 and 2. So as we can see here, that's A, right? Roman figure 1 and 2 only. These are the only true statements here. So look at how I actually figured out that, right? So you have to actually put your mind into solving those multiple choice questions. It's not just guesswork. Then consider the synthesis reaction of ammonia. The making up synthesis is making up of ammonia. The rate at which N2 is consumed during the reaction is X mole per dm cube. Which one of the following is the rate at which ammonia NH3 is produced in mole per dm cube with respect to N2? So I think this would have to be considering the ratios. So let's check now. If the ratio of N2 to NH3 is what? Is 1:2 according to our molar ratios, and then we are being told that this is being consumed at X mole per dm cube, then that means this would have to be produced at what? At 2X mole per dm cube. So which one is the correct answer? It has to be B. B is the correct answer, right? So awesome. So again here, we have earned ourselves 4 marks, right? So let's proceed. So this was quite nice. So let's look at the next half. Okay, so consider the following reaction at equilibrium. So this side here is blue, and then that side is pink. The solution is currently pink, meaning that the forward reaction would have to be favored. Concentrated hydrochloric acid HCl is added to the equilibrium mixture. So they're adding hydrochloric acid. Now we can see that the Cl minus atom is on this side here. So that means they're adding on the product side, right? So obviously, if you bring back your spectator ion H, then you can see that by adding the concentrated hydrochloric acid, you are actually increasing the concentration of the Cl minus ion. Which one of the following combinations correctly describe the effect that the addition of the concentrated hydrochloric acid will have on the equilibrium constant Kc and the color change of the solution, right? So will this have an effect on the Kc? Remember, we do know when it comes to chemical equilibrium, we know that Kc can only be affected by what? By a change in temperature. So Kc is only affected by change in temperature. Affected only by, so Kc only affected by change in temperature, right? So if you increase the temperature, decrease the temperature, that's the only way you can change the Kc value. So that means using that strategy there, we already know that C and D would be completely incorrect. So we're not even going to look at that option. So that means the correct answer lies between A and B. So now I'm using the elimination method here. Now, is it no effect on Kc, but the solution turns pinker? Or is it no effect, but the solution turns blue? Now, understand this. According to Le Chatelain's principle, this is what we know. If we're going to increase the concentration on the product side, then we have to favor the reaction that would actually use up the products that have been formed there. right? So that will kind of use up those particles. So now, obviously, we are increasing on the product side, and then we have to favor the reverse reaction so that this added concentration here of the hydrochloric acid can be used up. Now, by favoring the reverse reaction, we are actually promoting a color change to what? To blue. Because now remember, we are moving from product to reactant. So product had a pink color. And then if we are now moving more to the reverse side, then that means we are promoting the whole solution to be what? To be blue, right? So the reverse reaction is favored. And then that means the whole solution now turns what? Turns blue. So that means our correct answer is what? Is B. Okay, so that's how we came to that conclusion there. Okay, nice. Then which one of the following substances can be described as a Laurie-Brunstad acid? Okay, so we do know that carbonates are mostly bases, so no. Potassium hydroxide, one of the strong bases, so no. And then sodium chloride, nah. But then this one, we do know that this one is an acid because it usually forms when ammonia reacts with H2O. And then your ammonia is a base. This acts as an acid. And then considering our conjugate acid-base pair, we know that this acid donates its proton to that. And then this becomes the conjugate acid now. And then here we have the conjugate base, right? So this here, the ammonium ion mostly becomes an acid, right? So our solution for 1.7 is going to be C. Okay, then we have 1.8. It says consider the salt CH3CONA. Which one of the following combinations correctly identifies the hydrolysis reaction and the pH of the salt, right? So let's check this. So is it this that react with that? And then, so okay, most of the time we know that when we consider this, the CH3COONA, if we actually dissociate it, then it ends up being this, right? And then the Na plus. So now in order to check whether this is acidic or basic, normally what we do is we take this ion here and then we react it with water, which is what they did here, right? And then they say which one of the following combination correctly identifies the hydrolysis reaction. So the one that undergoes hydrolysis reaction will be this part here. And then when it reacts with that. So note that what happens here is that since we know that this one here becomes a conjugate base, then this would have to be an acid, and then the water here would have to donate the proton so that this becomes now that CH3COOH and then plus OH minus, right? So the OH minus here indicates that this is now what? Basic, as we did say that this becomes a conjugate base. So the whole OH minus proves that the solution is basic. But then when it comes to pH, we know that if a solution is basic, then the pH has to be greater than 7 according to our pH scale. So 7 is for neutral, and then below 7 it's for acidic, and then above 7 it's for basic or alkaline, right? So that means the correct one here would have to be what? A, right? So obviously we were not going to consider this 2 here, C and D. So the correct answer lied between A and B once more. But then the pH here now sets things apart, right? The pH has to be greater than 7, indicating that we have a basic solution, an alkaline solution. So, okay, once again, our answer here is A, right? Okay, not once again. Okay, let's move. 1.9, consider the cell notation of a galvanic cell below. And then they say what? Which one of the following reactions occur at the cathode, right? At the cathode. Now, obviously, we know with the cell notation, this represents what happens in the anode half cell, and this represents what happens in the cathode half cell, right? So now they're saying which one of the reactions is taking place there. Now we know that it can't be this one because it doesn't include all. Okay, so we have Mn2 plus weight. Let's look at, okay, so C and D. Now this is out of the picture because we are talking about the cathode, and this has mentioned things that are in the anode. So we're not even going to look at that. Now it's a matter of looking at A and B. So I think it's just a matter of notation here, right? It's a matter of notation. So which one of the following reactions occur at the cathode? Occur at the cathode. Now, if you look at your 4b table or your 4a table, then you know that this reaction, in actual fact, it goes like this. Remember, at the cathode, we have what? Reduction. At the cathode, we have reduction, which is a what? A gain of electrons, right? A gain of electrons. Now, according to this, we can see that the MnO4 minus here is actually the one that reduces to the Mn2 plus, right? So, okay, now don't be confused if you actually look at this, if you actually calculate here. So let me show you the calculation. Now you might be asking yourself that how does it reduce, because this is from negative to positive. So it wouldn't make sense to say that it's a gain of electrons, because as we can see, it's moving from negative to positive 2. But note that this negative here is actually for the whole thing, right? It is not the oxidation number of the manganese ion. So what we'd actually have to do here is to calculate the oxidation number of this one by simply saying MnO4 minus, then the whole oxidation number of this is -1. But then we don't know the oxidation number of manganese, so we're going to say X. The oxidation number of oxygen is 2, right? So how many oxygen atoms do we have? 4. And then we're going to say -2, and then all of this should be equal to -1, right? So now we're going to have X is equals to -8 is equals to -1. And then we can simply just take the -8 over to that side. It becomes -1 plus 8. And then this is X is equals to 7, meaning that the oxidation number of manganese in that permanganate ion is actually 7. So we have Mn7 plus, in other words here. Now this actually reduces, gains electrons, and then now goes to Mn2 plus. Now we can see this is a reduction. This is reduction because it's a gain of electrons. There is a what? There is a decrease in oxidation number. Decrease in oxidation number. So that's basically what happens here. So the correct one would have to be what? B. The correct one would have to be B. And then once again, we have our 2 marks. So that one could have gave you a run for your money, but then you could have checked it on your 4B table and looked at the format. Does it appear like that or that? Remember, with the reduction or the cathode, it always has to be taken exactly as it is. You don't flip it around. You only flip it for the anode, right? 1.10, a spoon is plated with silver Ag during the process of electrolysis. Now they say, which one of the following graphs best represents the concentration of the silver ions in the electrolyte over time, right? Now, this is an electrolysis process, and what we know about this process here of electroplating is that the rate of oxidation is always equal to the rate of reduction. So rate of oxidation equal rate of reduction. Now, if the rate of oxidation is equal to rate of reduction, it means concentration remains constant. Concentration remains constant throughout the reaction, right? So that means our correct answer there has to be what? So which graph here is representing a concentration that is remaining constant throughout the reaction? It has to be graph B, right? All of those are just, this one is representing a decrease, that one is representing an increase, this one is representing a gradual increase, right? So, but then the one that is representing concentration remaining the same is that. So that's how you could have went through your multiple choice question for a total of 20 marks. So make sure that you just check it like that, and then learn the skill of answering your multiple choice questions. You have to actually apply your mind to it and actually engage your content, right? So let's now move to the next question. Okay, so now we have question 2. It says, consider the organic compounds A to E below. And then we know the strategy, guys. I've shared the strategy so many times with you that if you are given such questions, the best thing to do is to first start by analyzing, right? So you want to actually list or identify the homologous series to which each compound belongs. So we have 3-methyl butanone, and then based on that suffix, we know that this is a ketone. And then here we have C3H7Cl. Based on that halogen, we know that this is a haloalkane, right? So it kind of makes things easier for you. And then this one here, alkane, obviously, single bonds between the carbon atoms. And then as we can see, it's a hydrocarbon. And then what about this one? We have triple bonds here, so it's an alkyne, right? And then this one here, we can see that it's cool. So it has to be what? Carboxylic acid. Carboxylic acid. Now 2.1 says define a functional group, right? So a functional group, we say it's a bond, an atom, or a group of atoms that determine the physical and chemical properties of an organic compound. Right. So that's it. A bond, an atom, or a group of atoms that determine the physical and chemical properties of an organic compound is known as a functional group, right? Then 2.2 says, write down the letter of a compound that contains a carboxyl group. Now, carboxylic acid is the one that contains carboxyl group. So you see now, it's just plug and play. So 2.2.1, 2.2.2 has the general formula CnH2n and then O, right? Now we know the one that contains that O. Obviously, it has to be what? A ketone, right? And then 2.2.3 has an empirical formula of CH2. So I kind of feel like they messed this one up because if we can check here, they say, okay, so let's check. Is there any with that? Because if we can look at that, this is 1, 2, 3, 4, 5, 6, 7, right? So we have C7, but then how many hydrogens? 1, 2, 3, and then 6, 7, 8, 9, 10, 11, 12, right? So this one obviously wouldn't actually have an empirical formula. I mean, wouldn't be simplified any further. So this would both be the empirical formula and the molecular formula. But then when we look at this one, this is C2, and then 1, 2, 3, 4, 5, 6. So this is H6. But then if you want to be simplifying this one, it actually becomes CH3. So I kind of feel like here they wanted to say CH3, right? So the one with an empirical formula of CH3 would have to be C. Would have to be C. So they kind of messed that one up. So when you are practicing, actually check that one up. Okay, so 2.3, how will the molecular mass of compound E compare to ethyl methanoate, right? Ethyl methanoate. Where is compound E? So this is compound E. Ethyl methanoate and this. So let's check. We have 1, 2, 3, and then ethyl with 2 carbons, and then methanoate 1, right? So ethyl methanoate is what? Is an ester. Now, obviously, this ester here is a functional isomer to this carboxylic acid. Remember, cake, right? Cake. Now, carboxylic acid is a functional isomer to an ester. Aldehyde is a functional isomer to a ketone. So how will the molecular mass compare? We would have to say it's what? Equal to. Why? Because compound E and ethyl methanoate are functional isomers. And then if they're functional isomers, it means they have the same molecular formula. And obviously, if something has the same molecular formula, they have the same molecular formula and therefore a same molecular mass. And therefore the same molecular mass. Right. So a mark for saying equal to, and then 2 marks for explaining that. So compound E and ethyl methanoate are functional isomers, meaning they have the same molecular formula, and therefore if they have the same molecular formula, they have the same molecular mass, because that would mean same number of carbons, same number of hydrogens, same number of oxygen atoms. Okay, so 2.4 now says write down the structural formula of compound A. So we know that we always have to start with the backbone, right? The parent chain. So butanone. So that's how many? 4 carbons. But then they say 3 methyl, right? So 1, 2, 3. I'm going to choose to count from the left. 1, 2, 3. And then stretch it out to put my methyl branch there. So it doesn't matter whether you put it below or above, as long as it's in carbon number 3. Then butanone. So obviously, we understand that in order for this to be a ketone, the functional group has to be in between, right? It has to be in between the carbon atoms. So this is where we would have the double bond oxygen there. And then here it is already saturated 1, 2, 3, 4. So we can't put any other thing there. So this is hydrogens like that. You just fill in your hydrogens. And then there we go. I believe that's the structural formula now, right? So in carbon number, so if we count it, this is carbon 1. This is carbon 1, 2, 3, 4. So as we can see, this becomes 3-methyl butanone. So there's no need for us to say butan-2-one, because there's nowhere else where it could have been, right? It was obviously going to stay in carbon number 2. So hence we don't say butan-2-one. We just keep it a butanone. Then 2 marks for that. Then we have what? 2.4.2. So this was 2.4.1. 2.4.2 says the IUPAC name of compound E. IUPAC name of compound E. That's easy. It's a carboxylic acid. So 1, 2, 3. It has to be what? What's 3? Propanoic acid. Okay. Propanoic acid. And then, okay. IUPAC name of compound D. Okay. Compound D. Where are we going to start numbering? So we have to start numbering from the side that is closest to the functional group. Now, obviously, we know that the functional group takes preference over the methyl branches, right? So that means we start numbering from this side, 1, 2. We can't number, even though we see that there are branches here, we can't number from that. So that's 1, 2, 3, and then 4. Now, where do we take it? Do we take it up there or down there? Remember, you always have to choose the path or the parent chain that will produce a lot of carbon atoms. So obviously, we're going to go with this one because we can see there's still 2 more carbons here. So that's 5 and then 6, right? So this will become what? So it's 1, 2, 3, 4, 5, and then 6. So that means the one that we are seeing there has to be the methyl branch or carrying in carbon number 4. But then now, how do we give the IUPAC name? Remember, we have to start with that disturbance there, or that methyl branch. So we're going to say for 2.4.3, we have in carbon number 4, so that's 4-methyl. And then what's the longest chain? Hex. So hex hex, and then where is the what you call the triple bond? It's in carbon number 2, so that's hex 2 wine, hex 2 wine. So 2, 4, 3, hex 2 wine. Okay, so yeah, that's how we were supposed to go about that one. And then, okay, compound B is a secondary haloalkane. Now we understand what they mean by secondary. It means that the halogen there is in between two carbon atoms, right? So the carbon with the halogen, let's put it this way, the carbon with the halogen is in between two other carbon atoms or is attached to two other carbon atoms. So they say draw the structural formula of compound B. So as we can see, we are only just given the molecular formula. So, okay, how do we draw that one if they say it's a secondary haloalkane? So we're going to start with our thingy there, 3 carbons, our parent chain. And then where should we put the chlorine now? Secondary. So it means it has to be here, right? So if it's a secondary haloalkane, that means the chlorine has to be attached. Look at this. It is attached to the carbon that is bonded to 2 other carbon atoms. That's what we mean by secondary. So you can have secondary haloalkane, you can have a secondary alcohol, right? So note that. Not only are alcohols primary, secondary, tertiary, also with haloalkanes, it happens, right? So there we go. It's like that. So it's a secondary haloalkane, and then the structural formula is supposed to be like that. So 2 marks. Nice one. So that was for 2.5. All right, so we have 2.6, which says using the molecular formulae, write down the balanced equation for the complete combustion of compound D. Right. So for compound D, as we have confirmed before, we said the formula was C7H12, right? So let's check. It's 1, 2, 3, 4, 5, 6, 7. And then how many hydrogens? That's 3 plus 2, 5, 6, 7, 8, 9, 10, 11, 12, right? So obviously it's following the formula CnH2n minus 2. So that's the general formula for alkynes. As we can see, how many carbons? 7. So here we're going to have 2 times 7, 14 minus 2. That's the 12, right? But then remember, when we are talking about combustion, or sometimes they refer to it as what? Oxidation. You always have to remember that the general formula for any combustion or oxidation is that it's a hydrocarbon reacting with oxygen gas to always give us carbon dioxide plus water, right? So the hydrocarbon can be in the form of an alkane, an alkyne, or alkenes, right? As long as it's a hydrocarbon only containing hydrogen and carbon atoms. And when it burns in excess oxygen, it always produces carbon dioxide and water as the product, right? So at this point, all you have to do is take this molecular formula, because always it must be represented in molecular formulae. Then you just go 2.6 is your C7H12, and then plus, obviously you're going to leave some spaces for you to balance. And then this is CO2, and then plus H2O, right? So just by writing that, you already have a mark, and then the balancing is the what will give you an extra 2 mark here. So, but then as long as you know the combustion there, let's say maybe you fail to balance, you can walk out with a mark there just by doing that. But then, okay, let's balance now. How do we balance? We use the Chow method, right? So Chow method means let's first balance the carbons, then the hydrogens, and then the oxygens. So we're going to go like this. How many carbons are on this side? That's 7. How many carbons on that other side? That's 1. Now, what number would I have to multiply by 7 for me? By 1 for me to get 7. It would be 7, right? So that means just before the carbon on this side, on the right-hand side. Remember, I balanced on the right-hand side. So that means just here, I must put 7. And then I go to the hydrogens. I say, how many hydrogens on this side? That's 12. How many hydrogens on the right-hand side? That's 2. The imbalance is occurring on the right again. So what number would I multiply by 2 to get 12? It would have to be what? 6, right? And then now I have to put it on the right hand side, so just before the H2O. Now, when I get to oxygens, I say how many oxygens on the left hand side? That's 2. And then how many oxygens now in total? In total, now that I've put the 7 and 6, how many oxygens are there in total? 7 multiplied by 2, that's 14. 6 multiplied by 1, that's 6. So in total, now I have what? 14 plus 6, that's 20 oxygens. Now the imbalance is where? On the left-hand side. What number would I have to multiply by 20? By 2 to get 20, right? So that's like saying 20 divided by 2. You have to multiply it by 10, right? Now, have to put it where? Where I see oxygen. So I see oxygen right here. And then there we go. So having to look at all that, you can see that now it's balanced. We have 7 carbons here, 7 carbons there, 12 hydrogens, and then also here 12 hydrogens, 20 oxygens now, and then 20 oxygens in total. So the left and right hand side is now balanced. And then if you have balanced like that, now you get another 2 marks, which makes it 3. Okay, so that's how you were supposed to go about all of this question here. So for a whooping 20 marks. So make sure that you just collect, when it comes to this topic here, just make sure you collect marks, right? Just make sure you collect marks, guys. Now let's move to the next one. All right, so now we are on question 3, physical properties. It says the relationship between boiling point and the number of carbons in straight chain primary alcohols. So that means they just investigated straight chain primary alcohols. Okay, it says the following curve is obtained. Define boiling point. So define boiling point according to your CAPS document, guys. So always make sure that when it comes to definition, you write them verbatim. So, okay, what is boiling point? Boiling point, we say the temperature at which the vapor pressure of a substance is equal to the atmospheric pressure. Yes, so that's how you actually write it. So 2 marks. What is the structural similarity between the alcohols that make this a fair investigation? Now, I think that's the one that they mentioned there. The fact that all the compounds investigated are straight chain primary alcohols. Right. So that's what makes the investigation fair, right? They're all straight chain primary alcohols. So we know that it is just based on their molecular mass, right? It is just based on their chain length, right? So now we know that we are only looking at one independent variable, which is the number of carbons or the chain length, right? And then 3.1.3, which van der Waals forces is responsible for the trend observed in this curve, right? Then obviously it has to be what? The London forces. The London forces. Now remember, you can't say, as much as we are dealing with alcohols, you can't say it is the hydrogen bonds. They are not the ones that are responsible here, right? Remember, all of them have hydrogen bonds. So you can't specifically say that the hydrogen bonds of this alcohol here are stronger than the hydrogen bonds of that alcohol. They all have one side of hydrogen bonding. And what's really affecting the difference here is the what? Is the chain length. And then the chain length, it's being affected by the what? By the London forces. Write down the IUPAC name of the alcohol with the boiling point of approximately 410 kelvins. So, okay, When we look at this, 410 would be somewhere there. So if we stretch it out, it's going to hit that point there. And then when we stretch it down, it goes to 5. So 5 carbon atoms, what's their alcohol? 5 is what? Pent. So pentan, 1 all. Remember, primary alcohol. So hence the 1 there. Pentan, 1 all. 3.2, another investigation is carried out to determine the effect of structural differences on the boiling point. The table below shows the different compounds and their respective molar mass that was used in this investigation. Which compound A, B, or C will have the highest boiling point? Right. How do we determine the highest boiling point? We know that butanone is a ketone. This is an alcohol, and this is carboxylic acid. Right. Now, obviously, dipole-dipole forces, this one are hydrogen bonds, so these are stronger than that one. But then when we compare alcohol and carboxylic acid, as much as they both have hydrogen bonds, the carboxylic acid has 2 sides of hydrogen bonding, which makes it the one that will have the strongest intermolecular forces, and therefore the highest boiling point, because we know that intermolecular forces are directly proportional to the boiling point. So the stronger the intermolecular forces, the higher the boiling point. So that means for 3.2.1, we are going with C. And then fully explain the answer to question 3.2.1. And that was 5 marks, right? 5 marks. So, okay, this is how you must go about it. Remember, I did mention that if we are dealing with compounds that have different intermolecular forces, you always have to think of this acronym ICE, right? Where you have to mention the intermolecular forces present, and then you have to compare strength of the intermolecular forces, and then finally you have to speak of the what? Energy required to overcome the intermolecular forces. So think along these lines. These are your key points. These are the key points that will give you marks. So mention the intermolecular forces present in each of those compounds that you are given. Compare the strength of the intermolecular forces. When you compare, you use words like it is stronger than, it is weaker than. And then speak of the energy required. More energy is required to overcome this. Less energy is required to overcome that. Right. So how do we put it now? For 3.2.2, we are going to say, so okay, following that structure, we are going to say compound A, which is butanone, has dipole-dipole forces. Dipole-dipole forces. And then we have compound B has 1 side of hydrogen bonding. And then compound C, which is a carboxylic acid, has 2 sides of hydrogen bonding. Now, remember when you are comparing more than 2 compounds, we are now talking about a trend, right? So when it comes to a trend, you have to put your point like this. The strength of the intermolecular forces, now we are here. The strength of the intermolecular forces increases from compound A to C, right? So we are saying the strength of the intermolecular forces increases, right? From this being weaker, this being stronger than the one in A, but then C being stronger than the one in B and the one in A, right? And then now we are going to speak of the energy. More energy is required to overcome the intermolecular forces, in compound C. Thus, now we understand why it has a higher boiling point, or why it has the highest boiling point compared to A and B. So compound A has dipole-dipole forces. Compound B has one side of hydrogen bonding. Compound C has two sides of hydrogen bonding. We have mentioned the intermolecular forces present in all of those compounds. Now we say the strength of the intermolecular forces increases. Intermolecular forces increases from compound A to compound C. More energy, so more energy is required to overcome the intermolecular forces in compound C. Thus, it has the highest boiling point. So, yep, that's it. So that's how you are supposed to go through this question for a total of 12 marks. So again here, this is another topic that allows you to just collect marks, right? So when it comes to your organic chemistry, guys, don't just give marks to charity. If there's a chance for you to just bag 100% on question 2, 3, and 4, just do that. Just do that. Okay, let's move to the next question. All right, so we have question 4. And then this is on organic reactions. It says, consider the 3 organic reactions, 1, 2, and Roman figure 3. And then we can see all that pentan 1-ene plus hydrochloric acid to give us organic compound P. Organic compound P now reacts with sodium hydroxide to give us a secondary alcohol Q plus the sodium chloride. And then again, the organic compound is used in another reaction 3, reacting with sodium hydroxide again, but this time it gives us three products, right? So it's organic compound R, the NaCl and H2O. Looking at this from whatever that we have discussed before and even in class, I did hint on you to say that when it comes to organic reactions, they will always give you the contrast between your hydrolysis reaction, which is occurring in substitution, and then also your dehydrohalogenation, which is in elimination. And this is exactly what we are seeing in reaction 2 and reaction 3. I've always hinted to that. So you know when you walk into an exam, you need to know the difference between those two, whether it be in terms of their reaction conditions, whether it be in terms of having to then show the balanced equation in terms of your structural formula or your condensed formula. You have to work there knowing those, right? Then 4.1.1 says, is pent 1-ene saturated or unsaturated? Obviously, it has a double bond, so it has to be what? Unsaturated. Unsaturated. And then our reason is that it contains a double bond. It contains a double bond between its carbon atoms. So it contains a double bond between its carbon atoms. And then 4.1.2, reaction 2, write down the type of reaction represented by reaction 2, right? Now, you don't have to be specific with that. I did say that if they just want the type of reaction, you stick to addition, elimination, substitution. Only if they say what type of addition or what type of elimination, that's when you become specific and give the actual name. But then here, they're just saying what type of reaction is represented by 2. We know that it has to be what? Substitution. How do we know that it's substitution? Because it forms what? An alcohol, right? So we know that it's just substitution. It's just taking whatever haloalkane that's in here, or halogen, meant to say, take the halogen, replace it by the OH, right? Take the halogen from here, replace it by the OH. Now, the halogen that was here was chlorine. As we can see, the OH is now forming the alcohol, and the Na here now has Cl. So that's sodium chloride. So we know that the organic compound P here contained what? Contained the chlorine. So there was a haloalkane. So that is a substitution reaction. But what about a reaction 3? Reaction 3, as we did say, it has to be what? The elimination reaction. Now, you wouldn't be penalized even if you came here and became specific, right? You'd still get a mark, but then I'm just saying it's not necessary. Substitution is hydrolysis. Elimination, we have dehydrohalogenation. Dehydrohalogenation. So for y'all who love to flex, that's how you'd write that. Then 4.1.4, structural formula of compound P. Structural formula of compound P. Now, obviously, we know that it's coming from the pent here. So whatever that we are drawing here has to contain 5 carbons. So this is 1, 2, 3, 4, and then 5. And then in order for us to have created a secondary alcohol, that means this one also had to be a what you call a secondary haloalkane. So it's up to you wherever you put it, whether you say, obviously, I prefer to just number from the left. So this is 1, 2, 3, 4, 5. Then that means my chlorine would have to be on the second carbon, right? Making it a secondary haloalkane. Now, how do I know that? Because even the product that has been created is a secondary alcohol. So there we go. So, yep. Nice. Okay, now they say, IUPAC name of compound Q. IUPAC name of compound Q. So this compound Q that it will be formed here. Now, remember with compound Q, that's an alcohol, right? So it's just a matter of where they Cl, you would replace by OH. And then what would be the name of that? Still, we keep the pent. So it's pentan-2-ol, right? So that would be the IUPAC name of compound Q, which is the alcohol. All right. Then 4.1.6 says, reaction 2 and 3 require the use of a strong base, right? Write down the condition that will prefer reaction 2 over reaction 3. Now we know reaction 2 is the substitution, hydrolysis. Normally here we need what? Dilute, strong base, and then what? Mild heat. But then for the elimination one, which is dehydrohalogenation, we need concentrated. So in both of them, we'll still be using the same base, strong base, which can be sodium hydroxide, it can be potassium hydroxide or lithium hydroxide. In this case, we used sodium hydroxide, as we can see. But then the one in here, it's dilute, and the one in here is concentrated. That's the difference. Concentrated strong base, and then here we need strong heat. I don't know if strong heat is actually a thing. Yeah, but then heat, strong heat, right? Then 4.1.6 will go with what? Dilute strong base, because that's reaction 2, right? Dilute strong base and mild heat. Mild heat. Okay, so those are the reaction conditions that would be needed for the substitution reaction, which is your hydrolysis. Okay, nice. Then we have 4.1.7. It says pent-1-ene and organic compound R are isomers, right? What type of isomer is pent-1-ene and organic compound R? With organic compound R, we know that since this is elimination, organic compound R must be an alkene as well, because remember, if we follow USA, SSS, USA, and then SU, we know that we are moving from a saturated compound to an unsaturated. Saturated to unsaturated is elimination. So we know that we are forming an alkene here. We know that we are forming an alkene. And then if we are being told about pent-1-ene, And then the alkene that it's forming here has to be a major product, meaning that major product means that the double bond will form in between the carbon atoms. So we have something like pent 2 in, right here. We'd have something like pent 2 in. Now versus pent 1 in that we are given. So what type of functional, what type of isomers are this? Type of isomers that we have would be what? Obviously, positional isomers, because the only difference here would be in the position of the functional group. Here we have the double bond in the first carbon, but here we have the double bond in the second carbon. So the difference here is in the position of the functional group. So we go with what? Positional. 4.1.7, that's a positional isomer. Positional isomer. Okay, the flow diagram below shows the conversion of butan-1-ol to butane gas. And then we are given butan-1-ol undergoing step 1 to form organic compound X, undergoing step 2 to form butane. And then the following chemicals are needed. We need concentrated sulfuric acid, we need platinum, we need hydrogen gas. So I guess it's in that order, right? And then using condensed structural formulae, write down the balanced equation and indicate the chemicals used in each step in the preparation of butane gas from butan-1-ol. Okay, so let's see now. They took the butan-1-ol. So obviously the first thing that they would have to do using condensed structural formula, guys, condensed structural formula. Now, normally, this is what I say. If you want to be able to actually draw or write a condensed structural formula, you can start by a structural formula. So you have 1, 2, 3, 4. I know it can be a bit tricky. So, but then you have to take your time with this, right? So we have butan-1-ol here. This would be the butan-1-ol like that. And then it obviously has to react with H2SO4, concentrated H2SO4. And then the reaction condition is concentrated H2SO4 and heat. So we know that this is a process which we refer to as dehydration. We are trying to take out the water molecule, right? So when it dehydrates, it will become this. It will become this. So obviously, we'd have to have a hydrogen coming out there from this one. And then we have to have the OH coming out from that. So therefore, there will be a double bond there. Like that. And then now the H and the OH will be a byproduct H2O. But then remember, you are supposed to write in terms of what? Condensed structural formula. So reaction 1, this is what will happen. Now, how do I write it? Look at this. Condensed structural formula. The first carbon, so note, the first carbon contains how many hydrogens? 3. The second carbon contains how many hydrogens? 2. The third one contains 2. And then we have this one contains 2. And then we have OH, right? And then this through concentrated H2SO4. And then heat here. And then what do we have? CH3. And then CH2. And then we have what? CH and then CH2. Plus what? Plus water. Okay, so that is the first reaction that we are going to have. That's reaction 1. That's reaction 1. That would be the condensed structural formula. Okay, nice. Now, let's go to reaction 2. Now, remember with reaction 2, we are now starting from that compound. So the compound that we had is that alkene now. So we have that alkene now. And then it has to react with what? With hydrogen gas, but then the catalyst needed there is platinum, right? Now, when it reacts with hydrogen, that means when this double bond breaks, the hydrogens will just fill in the spaces. So we have this. So breaking of the double bond, and then hydrogen fills in there. Another hydrogen fills in here. Right. So now we have the what you call. We have the butane now. Okay. So how do we indicate it? Reaction 2 is going to be what? Remember, we must write it in. The challenge here is that we had to write in condensed structural formula. So now we're going to have CH3. So this can be time consuming, but then 6 marks is worth it, guys. We're not going to leave those marks away like that. CH3, CH2, and then we have CH, and then CH2, plus hydrogen gas, under a catalyst platinum, and then we obviously have to have what? Heat. So also heat is needed here. And then this now gives us what? This in condensed structural formula, that's CH3, that's CH2, that's CH2, and then CH3. There we go. So that's your condensed structural formula now. So 6 marks in the bag just like that. So that's how you were supposed to go about answering that question for a whooping 18 marks. So make sure that you practice how to draw those condensed structural formulas. But then I've shown you a method. You can first start by drawing out your structural formulas and then just try to compress them into what? A condensed structural formulae. In that way, it works. You end up with your marks. But then what's important with this topic here is knowing your reaction conditions. It's knowing how to draw your structural formulas, your condensed structural formulas, right? So again, if you practice that one, you can easily get 100%. Nice one. So we are through with organic chemistry. Then now let's move to the real things. Okay. Okay, so now we have a rate and extent of reaction. Question 5. It says the reaction between excess hydrochloric acid. Note that they said the hydrochloric acid is in excess, right? So they even wrote it in bold, which should bring something to you. With zinc is used to investigate factors that influence the reaction rate. The balanced equation for this reaction is as follows. And then we are even given this. This indicates that we have an exothermic reaction. 3 experiments are carried out and 1 factor is changed in each experiment. The same volume of hydrochloric acid and the same mass of zinc granules are used in each experiment. The hydrochloric acid completely covers the zinc in each experiment. Define reaction rate. So here, concentration of hydrochloric acid is 0.5, here it's 0.8. And then in experiment 3, they bring it back to 0.5. But then the Cu here, I guess this one is the catalyst that they chose to use. So no catalyst, and then here there was. Define reaction rate. So what is reaction rate? We say this is the what? This is the change in concentration. Change in concentration of products or reactants. Okay, so let's say of reactants or products per unit time. So that's your definition. So from your CAPS document, so write it exactly as it is. Change in concentration of reactants or product per unit time, right? Then 5.2 says write down in an investigative question when comparing experiment 1 and 2. What would be the investigative question there? So when comparing 1 and 2, we can see that the factor that is being investigated there is what? Concentration. As we can see, our independent variable here is the concentration. It has been given in different amounts, right? So that means I would say, what is the relationship between the concentration and the reaction rate? And then since it's an investigative question, do not forget to put a question mark. So what is the relationship between the concentration and the reaction rate, right? 5.3 says the curve not drawn to scale is obtained for the volume of hydrogen gas and then produced over time for experiment 1. How does the rate at which hydrogen gas is produced between T1 to T2 compare to that of T2 to T3, right? So is it higher than, lower than, or equal to? Now, obviously, if in putting your lines here, you can see that the gradient here. Remember, when we are talking about the reaction rate, we are simply talking about the gradient of the graph. The reaction rate is just the gradient. So if we can just draw gradient lines here, we can see that this gradient is a bit sharper than that one, indicating that this here is a higher reaction rate, but then here this is a lower reaction rate or a slower reaction rate. So that means the rate at which the hydrogen gas would be produced between T1 to T2 would be much higher than the rate at which hydrogen gas would be produced between T2 to T3. At this point here, it's now coming to completion. Your reaction is now coming to completion, meaning that the reaction rate now starts to be slower, right? So 5.3, we are going to say this is actually higher than that. So it's higher than. Right. Okay, nice. And then, so there was just one mark, no reason. Redraw the graph in the answer book. Clearly label the curve as A on the same set of axes. Sketch the curve that will be obtained for experiment 3. Label this curve as B. So what's going on with experiment 3? With experiment 3, they've decided to add a catalyst. So we know that adding a catalyst would actually do what? Speed up the chemical reaction. So that means the gradient of curve B would actually be a bit steeper than this one. But then at the end of the day, they should all come to completion at the same amount of hydrogen gas, right? Because it's not like we are increasing the number of particles there. We are just simply having a higher reaction rate. So we would indicate that this is B and then this is A, right? So all we have to show there is that since there's a catalyst involved, that means the rate of reaction would be higher. And then how do we indicate that? By a steeper gradient, right? So this is a steeper gradient than that one. So B compared to A, we can say that B is a bit steeper and then A is a little bit smooth, right? So that's all you indicate. And then 2 marks for that. All right. So moving on to the next one. Now we have 5.4. It says the reaction in experiment 1 takes 58 seconds to reach completion, and the average rate at which hydrogen gas is produced is 8.39 centimeter cube per second. Calculate the initial mass of zinc used in experiment. In each experiment, the molar volume of hydrogen gas at 25 degrees Celsius is 24,000 centimeter cube. 24,000 centimeter cube per mole. Okay. Experiment 4 is now conducted by increasing. Okay. Am I still on the same question? Okay. This one is this. Okay. Then let's see now. Calculate the initial mass of zinc. So the first thing, obviously, we can see that we are provided with the reaction rate, and it is based on what? The volume. According to this SI unit, centimeter cube per second, we can see that the reaction rate has been given in terms of volume. So that's reaction rate is equals to change in volume over change in time. Now our rate of reaction is 8.39, and then we'd have to say final volume minus initial volume. So obviously the initial volume, if we are talking about the hydrogen gas, this is a product. So we're going to assume that no hydrogen gas had been collected initially, because obviously if in the graph says so, according to the graph, we can see that at T0 here, there is no hydrogen gas that is present in the reaction vessel. So that's 0. And then our delta time, what is it? How many seconds did they say this takes? It's 58. So we're going to put 58 here. And then we actually cross multiply to find the volume that has been produced, which according to our graph, we were not given because there are no values here. As we can see, no values. So we had to calculate that at the completion of the reaction, what is the maximum amount of hydrogen gas that has been collected or produced. So our volume now, when we cross multiply this, it becomes what? 486.62 centimeter cube. I'm actually going to leave it in centimeter cube because I see that everything here has been indicated in centimeter cube. So we might just as well fly with that. Now we have the volume. So obviously we know after this, that's when we start with our stoichiometric steps. I always told you with this kind of questions, if you just know the 3 stoichiometric steps, which is calculating the number of moles, comparing the molar ratio, and then calculate the required value, then you are done. So step number 1 now, this is when we start with stoichiometric step, is calculate number of moles, right? Calculate number of moles. And obviously we're going to calculate the number of moles of what? The one that we are given, which is hydrogen gas. So this is N is equals to V over Vm. The reason we are using this formula is because we are given molar volume, right? And then this will become what? N is equals to 486.62 centimeter cube, which will cancel out with this, right? So hence I'm not even converting there. 24,000 centimeter cube per mole, right? So centimeter cube and centimeter cube will cancel out. And then when we divide this, what are we going to get? It's 0.02 mole, right? So that's the number of moles. So number 1, calculate the number of moles. Number 2, now remember, what are we trying to calculate? Zinc, right? So number 2 is compare the molar ratio. Compare the molar ratio. Now, what molar ratio? We're going to compare the molar ratio of the hydrogen gas and what we are looking for, which is zinc. So this requires us to go back to the balanced equation now, right? Go back to the balanced equation. We look at hydrogen gas, we look at zinc. What are the molar ratios there? As we can see, the ratio here is 1, the ratio there is 1. The coefficients are the ratios. So 1 is to 1, meaning that also the number of moles of zinc need to be what? 0.02 mole. Remember, same ratio, same number of moles. Then, to then calculate the what? The mass of zinc. To then calculate the mass of zinc, now we have step number 3, which says calculate for the required value. Calculate for the required value. So we are going to have N is equals to mass over the molar mass. Our number of moles, 0.02. And then we have mass over the molar mass. What is the molar mass of zinc? From the periodic table, that's 65. When we cross multiply there, 0.02 multiplied by 65, we get that our mass will be what? 1.30 grams. And that's all. That's all you had to do. So 5 marks in the bag, just like that. Just like that, guys. Easy peasy. So maybe you could have got a mark for this one here, got a mark for this one there, and then compared the molar ratios, could have been a mark. And then you did cross multiply here, that could have been a mark, and then you got your answer there. So 5 marks like that. So nothing crazy, guys. Understand your 3 stoichiometric steps. Calculate the number of moles, compare the molar ratio, calculate for the required value. There is no crazy calculation when it comes to this. Again, here you can just score your 100%. So I'm giving you just question 2 to question 5. Score. And then maybe you can try to collect some marks in question 6 and 7. But then when we go back to question 8 and 9, score marks. That's how you pass your chemistry paper. question 2 to 5, and then skip the 6 and 7. You'll come back to it. Write 8 and 9. That's the strategy. Collect marks. Okay, so now we have a 5.4 or 5.5 meant to say experiment 4. So I believe this is the substatement. Experiment 4 is now conducted by increasing the temperature of the reaction mixture in experiment 1. So this is where we have to think now. What does an increase in temperature do to the reaction rate? We know according to our Maxwell-Boltzmann distribution curve, an increase in temperature actually increases the average kinetic energy of molecules. So also according to collision theory, right? And then how will this change affect the reaction rate? So that means we're going to go with what? Increases, right? And then how do we explain that according to collision theory? So this is how you go about with your collision theory. You're going to say at a higher temperature, the average kinetic energy of the particles increases, right? And then which means more particles will have sufficient kinetic energy to collide, because now the kinetic energy is now greater than the what? The activation energy. And then which leads to what? More effective collisions per unit time. And then thus increasing the rate of reaction. That's the explanation, guys. Put it like that. At a higher temperature, the average kinetic energy of the particles increases. More particles will have sufficient kinetic energy to collide, leading to more effective collisions per unit time, thus increasing the rate of reaction. Just like that. And then you have earned yourself 3 marks. So all in all, this question was for 16 marks. So again, easy to collect marks here. Could have collected your marks easy like that. So know your questions, guys. Know where you collect marks. That's the whole strategy. Let's move. Okay, so we have question 6. It says, consider the following hypothetical reaction at equilibrium. So it's just a hypothetical reaction. The A and B obviously do not appear in the periodic table. They just are there for any kind of element or compound that could be there. The data in the table below shows the equilibrium concentration of A, which is a gas, and B, which is a gas at different temperatures. Then 6.1.1 says, state Le Chatelier's principle. Then what is that? How do we state Le Chatelier's principle? We say Le Chatelier's principle states that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium. By favoring the reaction that opposes the disturbance. That's it. When the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that opposes the disturbance. Nice. Then 6.1.2 says, is the forward or reverse reaction favored at 200 degrees Celsius? So how are we supposed to see that? Obviously, we're going to check by the concentration that is formed there. So if we look at the concentration of A, 0.0125, it's actually smaller than the concentration of B, which is 0.8. Remember, how do you check whether a number is smaller or bigger? It's not about the number of digits that you have after the comma, but it's just about the number, that one number after the comma here. So it's 0.0, which makes this one smaller. This is 0.8, which makes it big. So in this case, we can see that the product side has more concentration, which suggests that the forward reaction is the one that is favored. So forward. And what's the reason for that? We're going to say at equilibrium, the concentration of B is greater than the concentration of what? Of A, right? So that's it. And then how will the equilibrium concentration of A at 200 degrees Celsius be affected by the following? Choose from increase, decrease, or no effect. Equilibrium concentration. How will the equilibrium concentration? Then if the pressure is increased, if we increase the pressure, remember an increase in pressure favors what? Favors the side with less number of gas moles. So this one favors side with less number of gas moles. And which side has less number of gas moles? It is the reactant side, which is the reverse, right? And then we were asked about the concentration of A. So what will happen to the concentration of A in that case? It means it has to increase. So our answer is increases. So you can always collect marks when it comes to these conceptual questions here. Maybe your struggle with your chemical equilibrium can be sometimes with this, but then you can always collect on those other questions that are just conceptual, right? So you wouldn't lose all the marks here. And then how will it be affected by addition of a suitable catalyst? Now, obviously, we do know that the catalyst does not do anything to the concentration of either the reactant or the product. The only thing that the catalyst does is to speed up the chemical reaction, right? So no effect. No effect. And then 6.1.5 is the forward reaction exothermic or endothermic? Is the forward reaction exothermic or endothermic based on this? Okay, so let's check. They say, how will the equilibrium concentration at 200 degrees Celsius be affected by the following? Okay, what is the basis of asking this question? Oh, okay, now I see. The 200 and now it has been increased to 300. So now they're asking, is the forward reaction exothermic or endothermic? Now, obviously, we have to determine based on what is happening. We can see from 200 to 300, they've increased the temperature. And now we can see that here, this one is now being favored because now there is an increase in concentration. But then with this one, there is a decrease in concentration. Now we know that an increase in temperature favors what? An increase in temperature always favors the endothermic reaction. So in this case, we can see that the reverse reaction has been favored, meaning that the reverse is endothermic, which makes our forward to be the what? The exothermic, which makes the forward to be the exothermic reaction, right? So the reverse reaction has been favored, meaning that the reverse reaction is endothermic, and therefore the forward reaction is exothermic. So they're obviously going to want us to explain that. So exothermic, then use the Chandler's principle and refer to the data in the table to explain the answer to question 6.1.5. Okay, let's get to it now. So now we're going to say number one, the concentration of A increases, right? The concentration of A increases. And then we're going to say according to Le Chatelier's principle, according to Le Chatelier's principle, an increase in temperature favors the endothermic reaction. And then we say reverse reaction has been favored. Reverse reaction is favored. Therefore, reverse reaction is favored. Indicating reverse reaction is endothermic. And thus, forward reaction is exothermic. And that's forward reaction is exothermic. When it comes to explaining, I just like to explain everything in detail, right? So I don't want my marks to be disputed there. Want you to give me my marks. All I want is marks. The concentration of A increases according to Le Chatelier's principle. An increase in temperature favors the endothermic reaction. Reverse reaction is favored, indicating reverse reaction is endothermic, and thus forward reaction is exothermic. So that's a full explanation there. And then, okay, now the calculation. Initially, 1.05 mole of bromine, Br2, are sealed in an empty container. The following reaction occurs at 1600 degrees Celsius. At equilibrium, the concentration of bromine is 2.0. At equilibrium, 2.075 mole per dm cube. The equilibrium constant Kc is 6.34 times 10 to the exponent of negative 4, right? Okay, so now they say calculate the volume of the container. Calculate the volume of the container. So let's just use the Kc first. So we have Kc, and then as we can see, they're both gases, so that means they make it to the Kc expression. Remember, what doesn't make it to the Kc expression is solids and liquids, because they always have a constant concentration, right? So we take their concentration as 1. So it's only aqueous and gaseous substances that make it to the Kc expression. So here we know that it's concentration of product, Kc generally, it's concentration of product over concentration of reactant. So our product is bromine, but then we have a coefficient of 2, which should be taken as what? An exponent. And then here we have Br2. Now, we don't take a subscript as an exponent. So you write it like that. What is taken as an exponent is the coefficient. So we are given Kc. It is what? 6.34 times 10 to the exponent of negative 4. And then are we given? They said at equilibrium, the concentration of bromine, which we are given Br2. So we don't have the concentration of Br, right? So we're just going to leave it like that. So we have the Br there. And then square. But then we have the concentration of the bromine 2 here, Br2. So this is 2.074. And then we can cross multiply it there. If we cross multiply, we have Br square is equals to 2.074 multiplied by the 6.34 times 10 to the exponent of negative 4. And in order to get rid of this, we need to square both sides, right? So just do your maths quickly there. And then that's your Br. So your Br is going to give us what? So 0.036 0.26 mole per dm cube. I'm actually going to leave it into like 5 decimal places like that. Don't want to round off as yet. So yeah, then now I can then do the rice thingy. So initial change equilibrium, yeah. Then simply gonna have that and then divide here. Okay, so let's say on this one I will have BR2, on the other one I will have BR, right? And then considering my ratio is what? According to this, the ratio is just 1:2. And then what is my initial? Mole per dm cube. So I'll just have it in concentration. Initial air concentration. Note that we are being told that at equilibrium, the concentration of bromine was this 2.074. So we have initial, we have change in mole per dm cube, and then we have equilibrium concentration again in mole per dm cube. So we were already told 2.074 right here. And then we calculated this one, which we're going to put it here 0.03626. But then since this is a product, we know that initially there was no amount of products there. So what's the change? The change is that it gained that concentration of 0.03626. And then in order to do this, to get this one, we have to apply our stoichiometry, which is I take this, multiply by 1, then divide by 2, right? So take this, cross multiply with 1, and then divide by 2 to get that. So if you do your maths there, 0.03626. So what I'm actually doing is this, guys. Don't be confused. BR2 is to BR. The ratio is 1:2. So the concentration here is 0.03626. And then here we have X. So I'm simply just cross multiplying there. And then divide by 2. And then my X is going to become what? So let me just write it here. 0.01813. Keeping it to 5 decimal places. So because this is a reactant, it's getting used up, I will say minus, right? And then obviously in order to find my initial, then I would have to say if I take this plus this one, then this would give me the initial. So to find the initial, I would have to say is the change plus the equilibrium, ice, right? Then if we add this 2 here, we get 2.09213, 5 decimal places as well. But then what is the question here? We are supposed to calculate the volume of the container. Now that we have the initial concentration, and then we were given the number of moles of the BR2, we can actually calculate now. So just here, let's just calculate it here. So we're going to use the formula. C is equals to N over V. We're going to say we have the initial concentration, which is 2.09213. And then the number of moles, they said it's what? It's, where is it? 1.05. And then over the volume. Now, obviously, what we need to do is say volume 1.05 divided by the 2.09213. And then the volume becomes what? 0.50 cubic decimeters. Oh, and then that's how you would have your 7 marks like that, right? So first you had to calculate with your Kc to get the concentration of the Br at equilibrium. Then you had to use the Rice method in order to fill in here and find the initial number of moles of the bromine, the Br2. And then from there on, just use C is equals to N over V in order to calculate that initial volume of the container there. So, yep, quite nice, interesting question. So 17 marks in the bag. So these are the kind of questions where if you don't get a total, at least fight to get at least about 60% to 70% of the question, right? Just fight for that. But then make sure that you have already excelled in question 2 to question 5. Okay, let's move. All right, so we have this question 7 here. It says sulfuric acid H2SO4 is a strong acid that ionizes in 2 steps as represented by the equations below. Then 7.1.1 says explain what is meant by a strong acid. Right, so we know that strong acid is an acid that ionizes completely in water. Completely in water to produce a high concentration of the hydronium ions. So your hydronium ions being what? H3O plus, right? So that's a strong acid, an acid that ionizes completely in water to produce a high concentration of the hydronium ions. Then 7.1.2, give a reason why sulfuric acid is referred to as a diprotic acid. Obviously, we know it donates 2 protons. And then write down the conjugate base of H3O plus. Conjugate base, so obviously we can see it has to go like that. So the conjugate base is water. And then 7.1.4, write down the formula of the substance that acts as an ampholyte during the ionization of sulfuric acid. Now, how do you identify that? It has to be an element or a compound or a substance that in one reaction it will act as a base, but in another reaction it will act as an acid. If we look at this one, your sulfuric acid is obviously an acid, and this is a base. And then here we have, this is a base conjugate acid, right? And then look at this. This is still a base, and then that is an acid. This here has to become an acid, and this a base. But if we can look at this substance here, in this reaction it acts as a base, in that other reaction it acts as an acid. Now one substance, in one reaction it acts as a base, and in another it acts as an acid. That's what we refer to as an ampholyte, right? So what is the substance that acts as an ampholyte? It's HSO4 minus. And then write down the formula of the substance. Okay, calculate the pH value, or they say sulfuric acid has a concentration of 0.1 mole per dm cube. Calculate the pH value after complete ionization. After complete ionization, this is what you must realize about this, right? Remember we said this is a diprotic acid, right? So if it's a diprotic acid, note how many hydronium ions that it will have after complete ionization. 2, right? So we are given the concentration of sulfuric acid, but what we need to understand is that the concentration of the hydronium ions produced will be twice. So for 7.1.5, note this with the diprotic acid. The concentration of the hydronium ions it produces is twice the concentration of that acid. So that means since we are given 0.1, we do not use that 0.1 for the pH. We still need to say 2 multiplied by what? By 0.1, and then we get 0.2 mole per dm cube. This is the value that we're going to be using to calculate our pH. So always note this. It's very important to note that with a diprotic acid, the concentration of the hydronium ions produced are always twice the number of what? It's always twice the number of that acid or that diprotic acid. So now to calculate the pH, Remember the formula? So to then calculate the pH, this is the formula. We are going to say pH is equals to negative log H3O plus, and then which is going to give us negative log, and then we put the 0.2. Punch in your calculator, you get a pH of what? 0.70. That's it. Awesome. So now you have your calculation question like that. So obviously, this is also another question where you need to be strategic with collecting your marks, right? If you can be able to collect your marks in all these conceptual questions and your easy calculations, then even if you missed that 7 marks, but then you would have collected 13 out of 20, decent mark, right? So we do know that if in that 7 mark, you wouldn't completely lose it, right? Then calculate the concentration of the oxalic acid. Now, obviously, this is a basic question. If it's 3 marks, formula substitution into the formula and the correct answer. What are we given? 1.2 gram of anhydrous oxalic acid, okay, is dissolved in water to make 50 centimeter cube, which is not in the desired SI unit, and then a solution. Then calculate the concentration. So 7.2.1. We do know that the formula to calculate concentration, if we are given the mass and the volume, can be this one. C is equals to small m over a big M multiplied by a volume, like that. So concentration is what? That's what we are trying to calculate. Mass is 1.2. The molar mass of this, so that's 2 multiplied by 1 plus 2 multiplied by 12 plus 4 multiplied by 16. All in all, that gives us what? 90 grams per mole. So we want to put it here 90. And then the V is for the volume, but then we're not going to put the 50 as it is. We need to divide it by what? 1,000, right? So this will give us what? 0.05, right? So 0.05. And then if we punch it into our calculator, what do we get? So let's quickly do it. So this is going to give us 0.27 mole per dm cube. That's it. So 3 marks. Formula, substitution into the formula, and the correct answer. That's all. Okay, so another one could have chose to just calculate the number of moles first, and then from the number of moles, you then calculate the concentration. So someone else could have chose to start it from here, and then from here, they went to use this formula. So still the same thing, guys. Still the same method. You could have worked it out like that. It would still be correct, right? You'd still get 0.27, if not a number closer to that, because considering the part that if you do round off here, it's obviously going to affect your value for the concentration. So which is why I just normally prefer that one, because I'll just round off on the final answer. Then, okay, now we have this one now, which is the only hard question in here, or the only complicated looking question. I wouldn't say it's hard, it just looks complicated. Learners dissolve X gram of sodium hydroxide, NaOH, to make 2 dm cube solution of sodium hydroxide. They transfer 25 centimeter cube. So to make 2 dm cube of solution, and then they transfer 25 centimeter cube of the sodium hydroxide solution to a volumetric flask and added distilled water to make a diluted 100 centimeter cube solution. They titrate 43.8 centimeter cube of the diluted sodium hydroxide solution against 25 centimeter cube of oxalic acid. So this is the part we are interested in, the titration. And then prepared in question 7.2.1 to reach the endpoint, right? So the balanced equation is this: calculate the mass X gram of sodium hydroxide that was used to make the 2 dm cube solution. So, okay, we are much more focused on the what? On the titration. So 7.2.2. Now, what is titration formula? The titration formula is the one that goes CAVA, CAVA, CB, VB. And then this is what? NA over NB, right? So we can look at the balanced equation here. There we go. Because for the NA and the NB, we are not really substituting the number of moles, but we are substituting the molar ratios, the coefficient values here. So this is the acid and this is the base. We know that a titration is between an acid and a base, right? So, okay, now what is the concentration of the acid? We told about the concentration of the acid. Remember, they said it's from 7.2.1, right? So we did calculate the concentration in 7.2.1. Note that this question always always depends on the question that is above. Always when you solve that 7-mark question, it always somehow depends on this question that you have answered above here. So concentration is 0.27. The volume, they said what? They titrate 43.8 centimeter cube of the diluted sodium hydroxide against 25 centimeter cube of the oxalic acid, 25 centimeter cube. So, okay, normally we know with this formula, we are not really much interested in having to convert this. Why? Because the SI units will cancel out each other. So let me just substitute it with the SI unit so that you see my point there. And then do I have the concentration of the base? No, that's what I'm looking for. And then they said the volume is 43.8 centimeter cube. So reason I'm not even converting those ones, it's because look at this. Centimeter cube will just cancel with centimeter cube. So at the end of the day, it's all the same. What is the coefficient value of the acid? 1. What is the coefficient value of the base? It's 2. Right. And then to then calculate here, we just need to cross multiply. That's CB. Cross multiply this, it's going to be 2 multiplied by 0.27 multiplied by 25, but then divided by what? By the 43.8. So you need to be very slick with your maths here. Remember, they don't really care what you do with your maths. All they want now is their final answer. So it's this. Cross multiply with that, and then this cross multiply with that, then eventually we'd have to divide by the 43.8, right? So you can just do it step by step if you want to see. Then all of this, when we punch it into our calculator, we get 0.308 mole per dm cube, right? And then now we want to calculate the mass x gram of the sodium hydroxide that was used. The sodium hydroxide that was used, which we know that the sodium hydroxide that was used was the concentrated sodium hydroxide. So this is where we need to pull up this. Remember, this is now the diluted one. They said diluted sodium hydroxide. But then the 2 dm cube was actually made out of what? The concentrated one. So which is now where we pull up the formula C1V1. So, okay, let me write what it means. The C1V1 formula is actually for the concentrated solution, and then this side is the what? The diluted solution. So when I say C1V1, I'm referring to the concentration when it's still concentrated and the volume when it's still concentrated. But C2V2, that's the concentration after dilution and the volume after dilution. So what I'm looking for here is now what? The concentration before dilution, which is when it was still concentrated. Now, they did mention that the volume was what? The volume initially was 25 centimeter cube. So where did they mention it? So they said, here is it. They transferred 25 centimeter cube of the sodium hydroxide. They transferred 25 centimeter cube, which that was when it was still what? Concentrated. And then to volumetric flask and added distilled water to make a diluted 100 centimeter cube. So they diluted it with 100 centimeter cube of that, right? Of water, of distilled water. But then it was only 25 centimeter cube when it was still concentrated. So this is what they tried to show there, right? So it was still 25 centimeter cube. Then we're going to have the 25 here. And then again, I'm not going to convert because it will cancel out. Then what's the concentration of this when it's now dilute? Remember, we did calculate the concentration of the diluted part, which is that 0.308. And then what was the volume that was used when it was diluted? It was what? So they diluted with what? They diluted with the 100. They diluted, when it was diluted, it now had an additional volume or additive volume of 100, right? So remember, it was the 25, and then they put in distilled water to make it 100, right? So that means they added 75 centimeter cube on top. But now as a dilute sodium hydroxide, it now has a volume of 100 centimeter cube. So walk with me. 25 and then 25. So concentration of the sodium hydroxide when it was still concentrated, divide all of that, we get what? 1.232 mole per dm cube, right? But fortunately, we are not done. We still need to calculate the what? The mass, right? Okay, to then calculate the mass, this is what we're going to do. So I believe you have written here. So the concentration C1 was 1.232 mole per dm cube. And now note that, what did they say here? So learners dissolve X gram of sodium hydroxide to make 2 dm cube solution of sodium hydroxide, right? Okay. To now calculate, we're going to use the formula. C is equals to mass over molar mass times volume. Concentration is 1.232. And then what are we looking for? That mass. What's the molar mass of sodium hydroxide? 40. And then the volume that they used, 2. Now we cross multiply here. It's 1.232 multiplied by 40 multiplied by 2. Then when you punch all of that into your calculator, you get 98.56 gram. Okay. So yeah, I know a lot of you saying that I could have just skipped that question. Yeah, for the ones that are interested in mastering this type of questions, I have done a couple of them, and then I will drop the link for the ones wanting to master this 7 marks type of questions in acids and bases. But I know a lot of you just saying in your hearts that, nah, they would rather just have those 7 marks to themselves. Yeah, but then you know what I advise? In each and every question, just aim to at least get 60% for the, especially when it comes to those calculation questions on acids and bases and also chemical equilibrium. Just aim to get at least 60, 70%, maybe by chance. Yeah, but then also just master on those other topics that do not require so much crazy calculations. So here you need to be really, really good with your stoichiometry and just understanding the whole process of titration. Okay, so let's move. So all of that was for 20 marks, guys. So acids and bases really has marks. So for people aiming for like 90%, your distinction, you have to actually know that calculation. That's what's actually would be stopping you from finding that level 7 or getting that distinction. So you really, really have to master this. Okay, now let's move to more lighter questions. All right, so we have question 8 on galvanic cell. It says a standard electrochemical cell is set up as shown below. They say 8.1 state the energy conversion that takes place in the cell. So, okay, we already know that for galvanic cell, the energy conversion is what? Chemical energy to electrical energy. So 2 marks like that. Now they say component Y ensures that the cell is complete. State one other function of component Y. So component Y, we know that it provides a path for the movement of ions. And then if you don't want to mention that, you can mention that it ensures electrical neutrality in the cell. So either one of those guys. Then 8.3 now says, write down the reduction half reaction. So, okay, let's first look at our 4B table. And then obviously here we are going to compare the PB2 plus and the Fe2 plus Fe3 plus. Now the platinum will not get involved because the platinum there is simply just an inert electrode. It is not actively involved in the redox reaction. Now we are using this platinum simply because we cannot choose any of the two here to be the electrode, since both of them are aqueous reactions. And then for the electrode, we need something that is a solid and can conduct electricity. So both of these are in aqueous state, and then therefore they cannot be able to conduct electricity, right? And therefore we employ now the platinum electrode, but then it has to be inert and reactive so that it doesn't affect the concentration of any of those, right? So it doesn't get involved in the redox reaction. Now write down the reduction half reaction. Obviously we know the determining factor here is that we have to look at our 4B table, and then the one that will be above is the anode, and the one that will be below is the cathode. And the cathode, that's where the reduction takes place. So, okay, let's check now. So we have this. So the PB2 plus, there we go. And then the Fe3 plus. So we have to take the one that exactly matches up with that. We can't take the Fe3 plus 2E to give us Fe because it doesn't exactly match up with that. Again, we cannot take out this one here. So it has to be the one that it looks exactly to what we are given in the diagram, right? Which is this. Okay, so this is the anode where oxidation takes place. This is the cathode where reduction takes place. So the equation that we are supposed to write for 8.3 is Fe3 plus E, and then just a single arrow. Don't use the double arrows because this is used to indicate that this can be oxidation and reduction. But then because we are only indicating reduction, we just write it from left to right and then indicate a single arrow like that. So, okay, that's what we have there. Okay, now what's the next question? They are saying calculate the initial EMF of this cell. So 8.4, we are going to say E cell is equals to E cathode minus E anode. And then this will give us what? Okay, so there we go. E cathode, that's at 0.77. E anode, that's at, what's this number here? Negative 0.13. And then when we punch all this into our calculator, we get 0.9, right? Or 0.90 volts. And then that's your E cell. So you have your 4 marks just as easy as that. So formula, the 2 substitutions, and then that mark with the SI unit. Okay. Now, they say choose from increase. How will the reading on the voltmeter be affected if the Choose from increases, decreases, or remains the same. If the initial, note this, if the initial concentration of the Pb2 plus is increased, if the initial concentration of the reactant is increased, now obviously this will put pressure on the cell to use up this, right? To use up that. And then if we use up that, that means we are favoring the what? The forward reaction. And if we are favoring the forward reaction, what happens to the voltmeter reading? The voltmeter reading will obviously increase, right? So for 8.5.1, if the initial concentration of this is increased, then we must have what? We must have the voltmeter reading increasing. So it increases. And then 8.5.2, what happens to the surface area of the PT electrode? Surface area of the PT electrode, will it increase, decrease, or remain the same if the surface area of the PT electrode is increased? Now, we don't know the surface area having any effect on the voltmeter reading. So we're just going to say remains the same. Remains the same. So it has no effect. Surface area has no effect, especially even given the fact that the PT will not even get involved. Remember, it's an inert substance. This is an inert substance. Shouldn't be actively involved. The Pb2 plus half side is now replaced with this, right? So what will happen to the voltmeter reading? Let's check now. So it's about looking at the distance now. So we are now replacing that with this. So if you can just check now, the distance from here to there versus the distance all the way from down here, we can now see that obviously, if you are to even do the calculation here, this would be 0.77 minus negative 0.76. Obviously, this will give a higher EMF value. So it has to be increases. Increases. All right, then explain the answer to question 8.5.3 by referring to the relative strengths of the reducing agents. Now, they want us to explain that, but not based on a calculation, based on the strength of the reducing agents. Now, how do we put that? So this is the nice part now. Okay. So going back to this, we are now going to say, as we can see here, this is about comparing the strengths of what? This is about comparing the strength of the reducing agents, right? Okay, no, the strength of the oxidizing agents. We are on this. We are on which one? Okay, let's see. Refer to the strength of the reducing agents. Okay, they did tell us, yes, reducing agents. Okay, so meaning we have to check this side. It's comparing this and this, right? So what are we going to say? Zinc is because as we can see, the strength of the reducing abilities from down here all the way to up there. So it's increasing like this. It's increasing as we go up the standard reduction table. So zinc is a stronger reducing agent than Pb, right? Which means zinc will oxidize. Remember, what does a reducing agent do? It oxidizes. Zinc will oxidize. Zinc will oxidize to zinc 2 plus. And that's all you mention. Meaning, and then more energy is released per unit charge between zinc, and Fe3 plus, right? So as we can see here, the distance, right? The distance. So that means there would be much more energy that is released compared to when it's Pb and Fe3 plus. So when it's zinc and Fe3 plus, more energy is released per unit charge, right? So that's how you actually put it there, right? So nice one. Okay, let's now move to the last question. Ah, okay, so we have question 9. It says a few drops of phenolphthalein are added to concentrated sodium chloride solution. The solution remains colorless. Carbon electrodes P and Q that are connected to a battery is dipped into the solution as below. Define electrolysis. What is electrolysis? We say this is the chemical process in which electrical energy is converted to chemical energy. That's it. Write down the name of the component that shows that the above cell is an electrolytic cell. Obviously, battery. And then they say, write down the name or formula of the gas produced at electrode Q. So this is positive and this is negative. So negative, remember when it comes to this, negative is the cathode and positive is the anode, right? At the cathode, what gas do we have being released there? The cathode, we know that we always have hydrogen gas being released, H2, or you want to say hydrogen gas. Always remember that with a concentration of, a concentrated sodium chloride, electrolysis of concentrated sodium chloride, always note that in the cathode we have hydrogen gas, in the anode we have chlorine gas. That's something that you always must remember there. 9.4, write down the half reaction that occurs on electrode P, the anode, right? So it's which one? So remember, we have two reactions there. It's this one for chlorine. Where is it? And then we also have another one. For water there, that has water and oxygen and all those things. Where is that? Where is it? Where is it? Where is it? Where is it? Yeah, here is it. So remember, if we are still keeping up to our 4B table, when we are dealing with an electrolytic cell, your question 9, when we are dealing with an electrolytic cell and we're still keeping up to 4B, now this becomes the cathode and that becomes the anode. That's one thing that you have to note, right? So now there is a flip of that. So the one that we are supposed to write is this. But then remember, oxidation is always written from the right going to the left. So that means we're going to write it as what? 2Cl minus to give us Cl2 plus 2E. That's the oxidation half reaction that occurs in the anode. Right. Now they say phenolphthalein is colorless in an acidic solution and pink in an alkaline solution. Write down the color of the solution around electrode Q and formula of the substance responsible for the color. So for 9.5, we are going to say it has to turn what? Pink. Why? Because we know that this one results in what? In OH minus. So write down the formula of the substance is the OH minus. So as we can see from here, look at this. So at the cathode, we will always have that OH minus there, which indicates that it is basic. Remember, according to your Arrhenius theory, a substance that produces hydroxide ions in water is what? Is basic. It's a base. Okay, then we have what? So that's it. They say now an electrolytic cell is set up for the purification of copper ore that contains zinc and platinum, PT impurities. After the purification of the impure copper was completed, 1.38 times 10 to the exponent of negative 2 mole of electrons were transferred. The initial mass of the cathode is 2 grams. Which metal besides copper will be oxidized? Choose from zinc or platinum, right? Which will be oxidized. Now, if we are looking for something that will be oxidized, obviously, we are looking for something that will be a stronger reducing agent. So between platinum and that, let's see. So where is platinum? So we have zinc here. And then platinum has to be somewhere below. So here is platinum, PT. So obviously we can see that zinc is a stronger oxidizing reducing agent. Is a stronger reducing agent. So this one stronger reducing agent, in this one weaker reducing agent. So which one will be oxidized? It's obviously zinc, right? So for 9.6.1, we are going to say zinc. Now, 9.6.2 says calculate the mass of the cathode after the purification. Calculate the mass of the cathode after purification. So obviously, we're going to start with this and then say for our copper, this is how. So they say after the purification of the impure copper was completed, 1.38 times 10 to the exponent of negative 2 mole of electrons were transferred. The initial mass of the cathode is 2 grams. So we know that the reaction goes like this. So they say this was transferred. So after the reaction, the completion. So okay, this one is undergoing. Okay, this one is undergoing a reduction. So it has to be like this. Okay. So now they say, when we compare this number of electrons, the number of electrons to the copper, we find that it is 2 is to 1. Now they just told us that 1.38 times 10 to the exponent of negative 2 mole was transferred of electrons. Then we're going to put X here because we are looking for the number of moles of copper. When we cross multiply, this is 1.38 times 10 to the exponent of negative 2, right? And then dividing both sides by 2, our number of moles of the copper now, since we can see that for every copper that is produced, then 2 electrons would have to be transferred. That means, what is the number of moles of this? If we do our calculation, that's supposed to give us 6.9 times 10 to the exponent of negative 3 mole, right? And then what is it that we want? The mass. So we want to use the formula N of copper is equals to mass over the molar mass. Now we have the number of moles of copper, 6.9 times 10 to the exponent of negative 3. We have mass, and then what is the molar mass of copper? Checking your periodic table will give you 63.5. And then when you cross multiply those, you're going to end up with what? 0.43815 gram, right? But then remember they said the initial mass of the cathode is 2 grams. So the cathode as it stands there. So remember, you had impure copper here, and then you have pure copper here. So the initial mass of this is 2 grams. And then now, this is the one that actually formed, right? So based on the reaction, this is the mass of copper that formed, or the mass of copper that actually reduced to this, right? So what are we going to now say? The mass of the copper finally is going to be the initial minus the one that is formed. Plus the one that is formed. And then that's 2 plus 0.43815. And then when you add those two together, then you get the mass of copper finally. That's 2.43815 grams. Hallelujah. So that's it. That's your whole Eastern Cape exam for a total of 150 marks. So that's how you were supposed to go about answering all this question, guy. So make sure that come back to this video, try to use it as your basis to practice, and then, as I'm doing, do the questions along with me so that you actually get to gain out of this. So make sure that you share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.